Okay, so this starts Unit 2, Atomic Theory, and this is Lesson 1. Today we are going to talk about how the evolution of the atom has changed from 1803 to today's modern theory, and what are the significant contributions that have been made by various scientists regarding atomic theory. So first let's give a definition of an atom. It is the basic building block of matter. And it cannot be broken down chemically. And the first person that we're going to mention is Democritus, who was Greek, as you can tell by his name. And this was about 450 BC. So this is a long time ago. And I don't test you on dates, and the Regents doesn't test you on dates. This is just to give you a chronological order of how things went down. And he tried to answer the question about divisibility of matter. He used the word atomos, which is where we actually get the word atom from, to describe the smallest particle of matter. And Democritus actually said that atoms were indivisible. Then along came Dalton, about 1803. So you've got a big jump, 450 BC, and the next person that we really give any credit to is Dalton in 1803. And he is known as the father of atomic theory. And he invented the word atom, probably from Democritus's atomos, as the basic unit of matter, which were considered to be indivisible. So he basically looked at Democritus's work, took the word atomos, turned it into atom, agreed with Democritus that the atom was indivisible. Now, he also made some other claims. Dalton claimed that all atoms of a given element are identical. So all atoms of oxygen are identical. All atoms of neon are identical. He also discovered that atoms of different elements have different properties and masses, which this makes sense because we know that neon is a lot different from oxygen and chlorine is a lot different from sodium. They have different properties and they have different masses. He found that combining atoms of different elements formed compounds. This theory is referred to as the cannonball theory. It looked like a simple sphere. So what does this name tell you about Dalton's atom? Well, if he referred to the theory as a cannonball and he's talking about the atom, what this tells us about the atom was that he felt everything was contained inside this ball. Okay, so now let's talk about J.J. Thompson. 1897. So not quite 100 years after Dalton. While using a cathode ray tube, he discovered that the ray was deflected due to the magnetic or electrical field. From this discovery, he concluded that atoms contain small negatively charged particles called electrons. Theory famously referred to as the plum pudding model. Because he visualized the electrons being embedded within the structure of the atom, just like raisin bread. So you guys aren't familiar with plum pudding, but you're familiar with rice pudding. So think of rice pudding with raisins. So he basically said that the pudding part was positively charged, and that the negative electrons, which were like the raisins, were distributed in the positive charge. The mass of the rest of the atom, besides the electrons, was thought to be evenly distributed, as I just said over here, and positively charged. After J.J. Thompson came Ernest Rutherford in 1909. So not so long after J.J. Thompson, a little bit more than 10 years. Now, Rutherford is famous for what's called the gold foil experiment. Where he bombarded a helium nucleus, where he bombarded a thin piece of gold foil with a stream of alpha particles. And this is often referred to as the nuclear model. Most alpha particles went straight through and some, when I don't even want to say some, and a minute amount, because it was so small, were deflected. So two conclusions were therefore made. One was that the atom is mostly empty space, and atoms have a dense positive central core, which you know today is called the nucleus. This experiment is extremely important. You see these asterisks? That means you really need to know this, okay? Before we move on, let me clarify something. So remember that Thompson said that the negative charges were embedded in the positive mass, which was the plum pudding model. By Rutherford doing the gold foil experiment, we have to realize how he drew his conclusions. So when the stream of alpha particles, now alpha particles come from a helium nucleus, and they are positively charged. So an alpha particle, as you'll learn when we get to nuclear chem, alpha particle is 4,2He. That's the symbol for it. And you can find this in Table O in your reference tables, which are the nuclear table. Since they're positively charged, what he found out was when some of them were deflected, he said that the reason why they were deflected is because whatever it hit had to be positively charged. So the nucleus had to be positively charged. So right there in this experiment, he proved Dalton's theory wrong, because if Dalton said that the positive and negative charges were evenly mixed, then that would mean that the nucleus would be neutral. And Rutherford found out that whatever was in the center of the atom had to be positively charged, because these alpha particles, which were also positively charged, were deflected. Now, what he also found out was the atom was made up of mostly empty space, because these alpha particles went straight through. And I'm going to show you a little video clip of that in class. So, moving on to Niels Bohr, looking at Rutherford's work, he proposed that the atom consists of a dense nucleus with the electrons found in well-defined orbits or paths. So he therefore stated that each electron orbiting the nucleus must possess a definite amount of energy to keep it in place within the orbital. And this